MBA 633 instructional video prepared by Professor Amit Datta, School of Management, George Mason University. In this video, we will continue our study of uncertainty by introducing the important concept of a probability distribution. Thus far, some of the concepts that we have introduced in connection with uncertainty are: what is an experiment, and what is an outcome, what is a sample space, and what is a random variable. So if you could just recall some of those terms, that will help in proceeding with this new concept. So whenever we hear the term distribution, it occurs in other contexts as well. For instance, students might be interested in the grade distribution in a course. So essentially what students are asking there is, you have different grades in the course, let's say A, B, C, D, F, and by a grade distribution, what students are essentially asking is how many A's were there, how many B's, how many C's, and so forth. Okay, so this is the y-axis. You can see is some estimate of count. How frequently did those values occur? So this is an example of a grade distribution. So alternately, people might be interested in income distribution. So there the x-axis is income, and people might be interested, how many persons make, let's say, $30,000 to $40,000. So how many? So again, this is a count. The y-axis is some element of frequency. How frequently do those values occur? Or how many people make within $90,000 to $100,000? Okay, so the term distribution refers to a pattern of values. So now that we have are encountering the term probability distribution, it should suggest to you that we are looking at some pattern of probability of uncertainty. So if you go back to a term that we had introduced before, namely a sample space is the set of all possible outcomes of an experiment. So if you think of running an experiment, it has a certain number of outcomes, and then if you ask yourself it, naturally you can ask the question, what is the likelihood of each of those outcomes? So if you can visualize a picture which tells you the probability or the likelihood of each of those outcomes in the sample space, the picture that you get is a probability distribution. Now, you already know from our prior discussion that there are two types of sample spaces, discrete and continuous. Therefore, it follows that there will be two types of probability distributions also, namely discrete and continuous. And in this video, we will focus on discrete distribution. We will look at continuous probability distributions later on. So let's pick a specific experiment, one that we have used before. So I walk up to a person at random and ask them which day of the week they were born. So this is the experiment. I walk up to a person at random and ask them which day of the week they were born. And we already know that the sample space consists of only these 7 outcomes. So no matter how many times you run the experiment, no matter who you ask, the output of running the experiment once is one of these 7 outcomes. So the sample space is those 7 outcomes. And then, to make it convenient for us to refer to these outcomes, we introduce the random variable x. X equal to 1 is a shorthand for a person reports their birthday as Monday. X equal to 7 is a shorthand for a person reports their birthday as Sunday. Okay, having set that context up, one can now ask the following question, or try to fill in the following picture. So I have this graph. On the x-axis, I put in the letter x, which is the random variable. It can take on the value 1, which is Monday, 2, which is Tuesday, 3, 4, 5, 6, and 7. So those are the outcomes of the experiment. Since this is a discrete sample space, I am able to enumerate these outcomes separately, individually, 1 through 7. And now the y-axis, the question I can ask is, what is the likelihood, what is the probability of each of those outcomes? And I represent that probability by the letter f of x or p of x, probability of x. Either one is fine. So the question we're asking is, what is the likelihood of each of those outcomes? Now, if I don't have any special information on which day of the week more people are born than others, if I don't have any specialized information, I could start off by saying that, well, it's equally, any of those 7 days are equally likely. Okay, if that's the case, then the picture of the distribution, the probability distribution I get looks something like this. My art is not so good, but these spikes should all be of the same height. And the height of each of those spikes should be 1 divided by 7. How did I get 1 divided by 7? The sample space has 7 outcomes. So notice once again how important it is to be able to enumerate the sample space. If I don't know the sample space, I can't really proceed with any probability calculations. So here I know that my sample space has 7 outcomes. I don't have any special information, so I'm saying, well, any of those 7 outcomes are equally likely. Hence, the likelihood of any one of those outcomes is 1/7, and the picture that we get over here is the one that you see before you, a bunch of 7 spikes, all spikes of the same height, and this is in specifically a discrete uniform distribution. Okay, and you can guess where the name uniform comes from. The heights of all the spikes are the same. Now, suppose I want to become a little more sophisticated and actually look at practical data. Okay, so I go back to, I visit some local hospital, or I access some birth data on the web, and this is the data that I randomly pick up 1,000 births from the papers or from the web, and I find that out of those 1,000 births, 50 of these people were born on a Monday. Okay, 200 were born on Tuesday, 275 were born on Wednesday, and so forth, 50 being born on a Sunday. Now, right off the bat, you can see from these numbers, this is what is a frequency distribution table, something that you've encountered before. So just from these numbers, you can see that each of those 7 outcomes is not equally likely. So what is the likelihood, probability of each of these outcomes? And that's very easy to compute. All you have to do is compute the relative frequency. So here we go. The relative frequency here is 50 for Monday is 50 divided by 1,000. Okay, and I can copy this formula down. So I get my relative frequencies, and if I add up the relative frequencies, I should get 1. All right. So this is the relative frequency. Now, once I have these numbers, so this is actually empirical data. I'm no longer assuming that each outcome is equally likely. I actually have data from hospitals or elsewhere that tells me otherwise. So now I can really be more realistic and draw the graph, my probability distribution. Once again, I have 7 outcomes, 1, 2, 3, 4, 5, 6, 7. And my probability, it no longer looks uniform, so I'll just draw a couple of spikes. So for x equal to 3, Wednesday, that's the tallest one, so that's 0.275. Okay, and then Thursday is 0.2, is a little bit shorter. Again, Tuesday is again a little bit shorter. Okay, so this picture that you see at the bottom is also a discrete probability distribution, but it's not uniform. Okay, so both these two pictures that you see in front of you, this one and this one, these are discrete probability distributions. Now, there are 2 properties that any discrete probability distribution has to obey. Okay. One, of course, is that probability cannot be negative. So you can't have negative spikes. So you can't have a spike that's below 0. Okay, all spikes have to be 0 or higher, have to be non-negative, and that follows from the definition of probability. We measure probability as a number between 0 and 1 inclusive. There are no negative numbers involved. Okay, so the first rule that has to be obeyed is f of x, which is the probability of any outcome x, has to be greater than or equal to 0. Okay, now the second one is the more consequential one, I would say, is that if you take each spike and you add up the heights of all the spikes over the sample space, the letter S represents the sample space. Okay, so this is your S. So in our case, S would be those 7 outcomes. If I added up the heights of the 7 spikes, you must get exactly 1, no more, no less. So these are 2 rules that any discrete probability distribution has to obey. Okay, so this is one example of a discrete probability distribution. Let's look at another one, an experiment that we had studied earlier. So here's the experiment. The experiment that I'm conducting is I pick up the Washington Post in the morning and count how many car accidents are reported in that day's paper. Okay, it's a little bit morbid, but it serves our purposes. So here you can see the outcomes of this experiment. So if you pick up the paper and you count how many car accidents are reported, maybe 0 accidents are reported. Okay, so none. Or maybe 3 accidents are reported, or maybe 4 accidents are reported. So the sample space, I think we have had this discussion before, could run from 0 to infinity theoretically. So theoretically, the paper might report an infinite number of car accidents. Of course, in practice, that won't happen. So now, if you use the analogy of the previous example, the graph, the probability distribution here, the x-axis, the x in this case, so x equal to 0 means the paper reported 0 accidents on that day. X equal to 1 means the paper reported 1 accident on that particular day. X equal to 2 means the paper reported 2 accidents, and this will go all the way up to x equal to infinity, theoretically, of course. Okay. So we can say x is 0, 1, that's one outcome, x is 1, x is 2, 3, 4, 5, so forth, let's say 11, and then on to infinity. Okay, so do you see the basic structure of the diagram is the same as that what we had before. The difference is this is also a discrete sample space. It's a discrete sample space because the experiment produces discrete outcomes. You can have 0 accidents, 1 accidents, 2 accidents. You can identify, enumerate each possible outcome. You can't have 1.5 accidents. Okay, so this is a discrete sample space, but unlike the previous example that we just saw, this is countably infinite. There are infinite number of outcomes. Okay, so on the x-axis, you have to account for an infinite number of outcomes. So x equals 0 all the way to infinity. And what do these so the y-axis is the probability of each of the outcomes. So again, what do? I collect some empirical data. Let's say I go back 1 year. I look at the Washington Post every day for the last 1 year, so 365 days. I look at those 365 days and I find that on 5 of those days, those 5 out of 365, the paper reported no accidents. Okay, on 100 out of those 365 days, the paper reported 4 accidents. So I've got my frequencies. Okay, so the first column is your x, your random variable, the number of accidents. The second column, number of days, is your frequency. Now you can compute the relative frequency. So as a practical matter, we are seeing that the paper has not reported more than 10 accidents in any one day. Okay, so essentially this is saying the probability of 11 or more accidents in a day is 0. That's from empirical data. So if I just look at these numbers, the relative frequencies here, again I will not draw all the spikes. The probability of x equal to 4 is 0.274. So let me draw that as the tallest. It's 0.274. The probability of x equal to 3 is 0.178. A little bit shorter. X equal to 5 is 0.151. So it looks something like this. Okay, so roughly if I were to draw the contours of this, it looks like this. Again, it's not a uniform distribution, but it's a discrete distribution, and even though there are an infinite number of outcomes, this distribution also has to obey these 2 rules. That is, every spike, every probability, every outcome, the probability is greater than or equal to 0. And if you add up all the spikes over the sample space, in this case the sample space is infinite, it has to add up to exactly 1. So you have seen here 2 examples of discrete probability distributions. Now, some patterns of discrete probabilities distributions occur with some regularity, and we will study those later. So for example, there are 2 discrete distributions called the binomial distribution and the Poisson distribution that occur in practice with some regularity. When the experiment meets certain conditions, those patterns of uncertainties will hold, and we will see them later on. But for now, I hope this gives you a sense of what a discrete distribution, probability distribution is, what that concept is, and what are the two rules that any discrete probability distribution has to observe.